Okay, good afternoon. In today's lecture, we're going to look at a technique for integrating composite functions, both the indefinite integral and the definite integral, but we're going to begin with the indefinite integral. So recall that when finding the indefinite integral, it's equivalent to finding the antiderivative of a given function, right? So if you have if you're considering a function that you want to take the antiderivative of, and that function is itself a composite, right, then you need to recall the chain rule. So recall that if you have some function of g of x, right, f composed of g of x, then the derivative of this composite is the derivative of the outside times the derivative of the inside. So in finding the reverse, right, if we want to look at the antiderivative of this, which is given right here, the antiderivative of that, well, then it's equivalent to the derivative of this side, which is just what's contained on the inside there. Okay. Now, this might seem convoluted and it might look messy, but trust me, when we start doing examples, you'll see that it's not so bad. In particular, we're going to focus on a technique called U substitution. So the technique that we're going to use is U substitution. Well, actually, what does your textbook call it? Your textbook calls it change of variables. Sometimes called U substitution. So, and this is a technique for figuring out how to find the antiderivative of these composites. And again, this is actually a theorem, but since this is more of an applied calculus course than a theory-based course, I'm not going to state the theorem. I just reference you to the textbook or any online resource to look at antiderivatives of composites or the change of variables there. Okay, so what does it mean to change variables? It means that we're originally looking at the antiderivative of some function of x, but to make things simpler or more simple, we're going to say that u is a function of x. And then if u is a function of x and we take the derivative of u with respect to x, we get that du is equal to g prime of x times dx. Like imagine originally it would be du over dx is equal to g prime. So you can kind of think of moving the dx to the other side and the du is that. So once you do that, you have that if g of x is u and du is equal to g prime of x dx, then this antiderivative is equivalent to looking at this antiderivative, where again, we're using the standard notation, the capital F. The derivative of capital F is F. F and capital F are, you can get from one to the other by taking the derivative of the antiderivative. So I think that the best way to describe this is with an example. So find the indefinite integral of x squared plus 1 all squared times 2x dx. Okay. Now with the techniques that we had prior, it wouldn't be so easy to find the antiderivative of this. But if we substitute u for g of x, where g of x is the inside of one of the functions, for example, it could be that, then when we evaluate the derivative of u and we kind of play around with looking for something that we know how to integrate, it tends to work out nicely, especially for the examples in the textbook. So let's just look at what happens here. So let's look at the solution, and we're going to use this change of variables technique. So we're going to say first, I'm going to notice that we can say let u be equal to x squared plus 1. Right, so then we have like some function namely x squared composite with u, because there's u right there, right? So if that's u, then du dx, or just du, is equal to 2x dx, right? If we treat u as a function of x, because it is, and do du over dx, it's equal to 2x. And then if you multiply both sides by dx, you get the du is equal to this. So then we can say that the antiderivative of this, let's just replace everything here by the representation with the variable u. That's what we're doing. We're changing the variables from x to u. So here we have that there's u squared, and then 2x times dx, well, that's just du. So then this indefinite integral becomes an integral in terms of u of this form. And we know how to find the antiderivative of something that looks like that, right? This is just equal to 1/3 of u cubed plus c. And don't forget that plus c. It's important because there's a whole family of antiderivatives of this function here. But we're not done, because the problem at hand is to find an antiderivative of this function in terms of x. There's no x's over here, but we can change back to our variable x by just saying, oh, what's u? U is x squared plus 1, so then we just put that in place of u. Okay, and it's that simple in this case, but we're going to see that sometimes it can be a headache trying to determine the right choice of u, and you might end up going down rabbit holes when you have a complicated looking integral to evaluate, and you have to really think ahead of time of what the end goal was. So for example, with this problem right here, I saw that the derivative of the inside here, the derivative of this, is actually equal to this. So once I solved that, I kind of had a clear choice of what my choice for u should be. So that once I pick my u, I take the derivative, this becomes du, and then I just have u to the power 2, and I know how to find the antiderivative of u squared. Right? So let's look at another problem. Find the indefinite integral of maybe 5 sine of 5x dx. And again, the du, the dx is just telling you the variable that you're taking, that you're integrating with respect to, right? So this is a indefinite integral with respect to the variable x. So again, this is a composite, sine composed with the function 5x. And that immediately makes me think, okay, if the inside is my u, and I take the derivative of the inside, what do I get? I get 5 dx, right, if that was my u. So then I see a clear choice for my function u. So I'm going to say, let u equal to 5x, then du is equal to 5 dx, right? And again, if typically you would write it like this, you would write du dx is equal to 5. But this implies that du is equal to 5 dx. Okay. So now once we've done that, we can interchange these variables in the original indefinite integral and then integrate with respect to the variable u. So then this would become, so I see a 5 times sine 5x times dx. Oh, 5 times dx is just du, and then sine of 5x is just sine u, so I can rewrite that as follows. So it's going to be equal to sine of u, and then 5 times dx is du. And now we know how to find the antiderivative of sine, right? This is just cosine of u plus c. But then again, we were originally asked to integrate with respect to the variable x. There are no x's here, so we have to look back to what u was and plug back in so that the answer is back in terms of the variable x. So it's 5x. Okay. So again, it really is like a game of picking the right choice and then looking back to the original problem and trying to get everything into a nice, clean form in terms of u that you know how to integrate with respect to. Okay. So I'm going to go ahead and pause the video and erase, and then we'll do some more examples. Okay, so let's look at another example where this one is a little bit more tricky, but again, it's still not bad. It's just, it really is like piecing together a puzzle. So I see that I have x times root of some other function of x. So my first choice here, my only clear choice to use change of variables or u substitution is to suppose that u is this linear function 2x minus 1. So maybe I can say let u be equal to 2x minus 1, right? So then as before, let's find du. So then du is equal to 2 dx. Okay. But now notice that I don't have any 2 dx over here, right? I eventually want to substitute in du somewhere, but I do not see 2 dx anywhere in there. So then what I can do is say that, well, 1/2 of du is equal to dx. And now I see that dx is really 1/2 of du, so then I can get rid of that dx and replace it with 1/2 of du. For the root of 2x minus 1, I can replace that with root u, but then I have x. There's an x left over. But that's okay, because u is equal to 2x minus 1 right here implies that what? X is equal to u plus 1 over 2. So at this point, I can replace that with this. I can replace this with that. And now I can replace x with that. I've changed every x up there, I can now replace with some version of u. So then the indefinite integral here is equal to, be careful. All right, so first I'm going to get rid of x and I'm going to replace it with that. So u plus 1 over 2. And so that's my x. And then I have root of that, but that in terms of u is just root u. And then dx, so this is root 2x minus 1 right there. And then dx is really 1/2 of du. So that would be my dx. So now let's combine these terms and factor out constants and see if this is something that is easy to integrate. Well, I see a 1/2 here and a 1/2 there. Those multiply together to be 1/4. So I can then take out that constant in front of the integral, and I can rewrite this as, say, 1/4 of the antiderivative of. And also, just for convenience, I'm going to rewrite root u as u to the power 1/2. Okay, it's starting to look a little bit nicer. So then I'm going to distribute in. So this would be u to the power 1/2 times u, which is u to the power 3/2 plus u to the power 1/2 du. Hopefully we can make out that 1/2. Okay. So now we just apply the power rule for integration on both of these u's. And I get that this is 1/4 times stuff plus your constant of integration. So what is that? So if I add 1 to that, I get 5/2, which is, I divide by 5/2, I get 2/5 of u to the power 5/2. Plus, if I add 1 to that, I get 3/2, right? And if I divide by 3/2, I get 2/3 of u, and then I have 3/2 there. Okay. So then finally, I need to send in this constant now. So this would be 1/10 of u to the power 5/2 plus 1/6 of u to the power 3/2, and then don't forget your constant of integration. However, again, and as before, we were asked to evaluate this indefinite integral with respect to the variable x. I don't see any variables x here, so I need to look back to see what u is, and then plug that back in. So u was 2x minus 1. And there's the final answer. Make sure you can read that. Okay. Okay. So I'm going to pause the video again, and then I'm going to write up the definite integral version of what we've been doing. Okay, so next we're going to consider how we can use the same change of variables technique for these definite integrals. Okay. Now, the general idea is the same with one very important exception. So as before, we have a composite derivative dx, and we choose u to be g, just like we were doing. So then, if there were no limits of integration, we would do exactly as we did before. We have f of u du, and then we integrate with respect to u. However, definite integrals are determined by their limits of integration. Definite integrals are a numerical value, not a function, right? So when you're taking definite integrals with respect to the variable x, your limits of integration are in terms of x. So when you make a change of variables to rewrite your function in terms of u, right? And you're now integrating with respect to u, your limits of integration need to be in terms of u, not x. Okay? And the way that you do that is quite simple, right? Because you want to know when x is equal to a, when x is equal to b, those limits of integration for the original definite integral. Well, u is a function of x. So if you've made your change of variables and now you're integrating with respect to u is some function of x, and you can simply evaluate u or g. So u is just g, right? Evaluate g at a and evaluate g at b, and those will give you your new limits of integration. So for example, here we have a composite type function that we're wishing to integrate on, definite integral, and we have limits of integration in terms of x, we're integrating with respect to x. So let's look at the solution to this. So first, I'm going to note that the only obvious choice for u would be 2x minus 1 as the inside of some composite. So then I would say maybe like let u is equal to 2x minus 1. And then as before, we're going to play this game of replacing everything in terms of x with the u, right? Every variable x with some version of u. So then immediately I see that du is equal to 2 dx. I do not see a 2 dx anywhere in that statement, but I do see that, that this gives us that 1/2 of du is indeed dx. So then, in a sense, I've accounted for that, and I've accounted for that. Now I need to account for that. In other words, I need to solve for x in terms of u. So then also x is equal to u plus 1 over 2. So now I've accounted for this piece as well, and I can rewrite this entire definite integral, what we're integrating on in terms of u, but now I need to also change the limits of integration. So then, so just note that u is equal to g of x, which is that thing right there. So then g of 1, the lower limit of integration, is going to be 2 times 1 minus 1. Oh. All right, so let's see. So this would be 1, and then g of 6 is equal to 2 times 6 is 12 minus 1 is 11. Okay, so by the way, just for convenience, I'm going to write this like this. Okay. So let's see if we can rewrite this. All right, so our new limits of integration are 1 and 11. And then we have x, which is really u plus 1 over 2, right? Times u to the power of negative 1/2 times dx, and dx is really 1/2 of du. Okay, so far we're following the rules. I'm going to factor out the this constant 1/2 here times that 1/2 is a 1/4. And then I'm going to have u to the power of negative 1/2 times u. So that, what is that? U to the power 1/2 plus u to the power negative 1/2 du. I think that's correct, right? 1 plus a negative half is definitely a half, and then that times that. Okay, everything is looking all right. So then we're going to have 1/4 times. So we add 1 to that, we get 3/2, and we divide 2/3 of u to the power 3/2 plus, if we add 1 to that, we get 1/2, and we divide by that, we get 2 u to the power 1/2. And this is evaluated from 1 to 11. Okay. So far, so good. So what does this become? A big old mess. That's what it becomes. All right, so it's this evaluated 11 minus this evaluated at 1. Let's see. So 2/3 of it's a half right here minus. Luckily, this one is a 1, so this is just going to be 2/3 plus 2, all of that times a fourth. Okay. Just keep on simplifying. So then we get that's a big number. There might be an easier way for me to do this. Let me look. I'm looking at like evaluating this numerically, evaluating that numerically. This is where having a calculator sometimes helps, but even then, there's only so much I can do with those 11s. Let me make sure that's correct, by the way. There's a 6. So 2 times 6 is definitely 12 minus 1. Yeah, it's 11. The other one is a half. Minus, and then 2/3 plus 2, what is it? So negative 8/3. So this becomes 1/6. 11 or 3/2 plus 1/2. 11 plus 10 to the power 1/2 minus 2/3. Whatever that answer ends up being. I don't have a calculator on me. Whatever that ends up being. Okay. All right. So I think I'm going to, before I stop the recording though, I want to say try on your own, maybe try this. Maybe try use that function of x and see what the answer, if the answer is easier to evaluate than this. From what I can tell, I don't think that I made a mistake in anything that I was doing. And if I did, I'll fix it after the recording is done and then upload another recording. But from what I tell, nothing is incorrect. But I have a suspicion that maybe if you try u equals to this, then the answer will be easier to calculate by hand. Because then the limits of integration are going to be smaller. And yeah. Okay, so I'm going to stop the recording here.